So what I wanted to say on the sideboard over here, just to get us started, is about spheres. You can think of this as sort of like a tiny little piece of background information that's not a big deal if you haven't seen before. So spheres. So the spheres come in all dimensions, all positive, non-negative dimensions. The most familiar example is the one sphere, S1. A lot of people call this the circle. And it's the set of points in R2, so it's a subset of R2. It's all the points that are a fixed distance from the origin. So a picture of it like this. And then the next dimensional sphere is the two-sphere, S2. It's a subset of R3. And it's, again, the set of all points in R3 that are a fixed distance from the origin. And the picture looks sort of like the following. So this is the two-sphere. And if you think about R4, which I recommend, then the set of all points in R4 that are a fixed distance from the origin forms the three-sphere. And drawing a picture of the three-sphere is part of what this talk is about. Maybe I'll just point out for the sake of, I don't know, completeness, there's also the zero sphere. It's a subset of R1. It's all the points that are unit distance from the origin in R1, and that's just 2 points here. One of the things that's interesting is that if you look at the intersection of the one sphere with the line, R1, you find out that there's a little zero sphere sitting inside there. These 2 points sit inside of the one sphere. And in the same way, if you look at S2, the part of the two sphere that intersects the xy plane, you see a little one sphere sitting inside of there. It's a copy of the one sphere that sits in R2. And likewise, if you look at the part of S3 that lies in, say, well, in the subspace, which is R3, then you'll see a little copy of the two sphere sitting, sort of an equatorial two sphere. And then other layers of S3 will be sort of other two spheres. So, okay, so this talk is about spheres, and it's about fibrations. So the next thing I want to talk about is what is a fibration? So the short answer to this question is fibration is a twisted Cartesian product. Maybe everyone here has seen the Cartesian product before, but I just want to sort of remind you briefly, right? So the Cartesian product is the set of all pairs of things, right? So product. So if you have a set A and another set B, you can form the Cartesian product of A and B, and it's just a new set which is formed by pairs of things. So if you have maybe 1, 2, 3, and B is the set, I don't know, U, V, then their Cartesian product has 6 elements in it, and those elements are 1, U, 2, U, 3, U, and then 1, V, etc. up to 3V. So 6 things. If you take the Cartesian product of the real line with itself, you have a set of all pairs of real numbers, so that's R2, the Cartesian plane. And it gets its name because it's a Cartesian product of these two. So often depict this by just drawing the x and y axes, right? So this is maybe one copy of the real line, and this is another copy of the real line. But of course, these two lines aren't the Cartesian plane. What we realize is that the Cartesian plane is formed by all copies of the line over here, and all possible copies of the line going up and down in all directions. Another example I want to talk about is the Cartesian product of the real line with the circle, with the one sphere. Is it clear to people what that is? Somebody can tell me? Yeah, it's an infinite cylinder. Maybe if I draw one copy, so this is sort of a copy of the real line, And here's a copy of the circle. Then the infinite cylinder is, well, circles out this way and lines.
You mean infinite hollow cylinder?
Yes, it's hollow. And that's key, right? Because this circle is hollow. Good. How about S1 cross S1? Is everyone familiar with that also? So this is a donut shape, the torus. And again, you could draw sort of two particular copies of maybe this sphere is the one that goes around that way, and that sphere is the one that goes this way. But really, the torus is made of sort of all of these copies all together. Okay, so those are Cartesian products. Now I want to talk about fibrations. Oh, before I do that, I want to give one observation about the structure of Cartesian products. So, a Cartesian product has a projection map. So, you can project from A cross B down to B by just forgetting the first coordinate of every pair of things here. And well, so that's pretty easy. The thing that's interesting about it is to try to go backwards. So if you take some element of B, little b, and ask, what's the set of all things that project down to this one point? Well, it's all the things whose second coordinate is B. So it's everything of the form A cross the one-point set of B, which is essentially A. So what you have is a copy of A lying over every element of B. So because so this is called the fiber over B. It is the copy of A that sits over this point. And because the fiber over every point is essentially the same, it's essentially A, then we mark that by putting an A over here to show that A is the fiber. So the fibration is something that has a projection like this. So of course Cartesian products are examples of fibrations, but there are fibrations that are not Cartesian products. So the idea here is you have some thing which you call the total space, and you have a projection from that thing down to some space, maybe it's the two-sphere, the base. So this projection is called P. And the property that makes this, so this is just a continuous function from one space to another, and the property that makes it a fibration is that if you look at and you point, and you ask yourself what's the set of all points in the total space that project down to B, it looks like some single space F crossed with that one point B. So this F is the fibers. And there's a slight sort of additional technical condition, so technical. It says that, in fact, if you take a little neighborhood of B, which we'll call D, and ask about the set of all points that project down to that neighborhood, that also looks like a product. So F cross D. Okay, so in small regions, this projection looks like the projection of a Cartesian product, but it doesn't necessarily have to be a Cartesian product altogether. Okay, so we describe this by saying that F is the fiber, because each of these fibers is just a single space F. Maybe, as an example, that fiber could be a circle. And then the total space, E is the standard letter to use for the total space. So now I want to give you a couple of examples of things that are fibrations, but not products. Yeah?
Just one small issue. If you told us what the pre-image is of every singleton in capital B, doesn't that uniquely determine what the map is? You told us that the things that map to little b are precisely F cross singleton B.
Yeah, so I've told you maybe up to homeomorphism.
Oh, whatever it is
in fact,
homomorphic to F cross singleton.
Yeah, and in fact, maybe what I really mean is homotopy equivalent.
So it's not exactly that set, it's something with the same properties as that set.
Something like that. Yeah, okay. That's the right idea. So let me draw these examples, and I think that'll help make it a little clearer. So the first example I want to draw is the Mobius Fan. It's a great example of lots of stuff. Okay. So here's the Mobius Fan. And there's a projection from the Mobius band to a circle. If you want, you can think about the circle that runs through the center of the Mobius band. And you can think about just collapsing to that circle. Every one of these, well, right, there's a vertical line above every point on this orange circle. This is the orange circle. And that vertical line is the fiber. So the fiber here is this vertical line. If you take any point here and look at its pre-image, you get this vertical line. And moreover, if you take a point on the circle and just look at a little neighborhood, so I'll call this D, so just a little neighborhood around this point, what do you see up above it? What's the set of all points that map to it? Well, there's a vertical line that maps to that point. And then, in fact, at every point on this little interval, there's a vertical line that maps to the corresponding point. And so above this interval, you see something that looks like, maybe I should have drawn it this way. Something that looks like a little, a vertical interval cross with this horizontal interval. Okay, so a little square. And if you've played with the Mobius band, you know that by just handling it, you can see that everywhere on the Mobius band looks roughly like this. The thing that makes it not a Cartesian product, of course, is that if you take one of these little intervals and imagine pushing it around the Mobius band, it flips upside down as it goes around. And that's the twisting that distinguishes fibrations from this special kind, which are Cartesian products. So I've talked about the Mobius band before. What I want to talk about today is, well, the Hopf vibration, and the first sort of transition there is to talk about another kind of vibration that's called the Hopf link, the Hopf band. So a different kind of band. The Hopf band is orientable. Mobius band is not. The Hopf band is, and basically what you get to make a Hopf band, imagine two circles that link with each other just once, and then imagine filling that in with a band. Okay, so how do you do that? Well, just imagine sort of filling in these lines here. Okay, this goes around and switch colors for the back side. Okay, and then it flips again, and we get orange. And then so that's a picture of a Hopf band. And in the same way, there's a center circle that you can project to. This one here. And the fibers are, again, little intervals. So maybe the interval from 0 up to 1.
So is that little interval flipped over twice?
Yes. And so this fibration is even harder to distinguish from a Cartesian product because as you go around the band, you flip once, and then you flip again. And so you end up looking exactly like you looked before, but the trick that you took was different from right? Here's the Cartesian product. Right? This is the interval cross S1. Okay, so the old adage, it's not where you go, it's how you get there. Right? So how you get there matters, and it distinguishes the Hopf band from this Cartesian product, which is the sort of the boring band. I shouldn't say boring, but it's interesting in its own right. So those are two examples of fibrations. Now, of course, the main example of the night is the Hopf vibration. it's a fibration of spheres. What I mean is not just some of the spaces involved are spheres, but in fact all of the spaces involved in Hopf fibration are spheres. The base is the 2 sphere, S2, and the fiber is the 1 sphere, S1, and the total space is the 3 sphere, S3. And so by understanding the structure of this fibration, because we understand the 2 sphere and the 1 sphere pretty well, if we can see how they're glued together, this can give us some insight on the structure of the 3 sphere. So that's one of the motivations here. The name for the projection from the 3 sphere to the 2 sphere is eta. That's the canonical choice. So what I want to talk about now is how this map eta is constructed and how to see the structure of the 3 sphere by understanding the structure of the Hopf fibration.
Can I ask a silly question now?
Sure.
So this is like a special thing about the 3 sphere, or are there other spheres that you can fiber over spheres?
Oh, yes, I'm so glad you asked that question. So there are some other spheres, and the list is pretty short. There are 2 others going up in dimension and 1 going down. So the circle is fibered over the circle, and its fiber is a 0 sphere. This is 0. This is just a multiplication by 2 map. Have you ever taken a rubber band, twisted it once, and folded it over? That's this map. The next one goes, let's see, the S4 from the 7 sphere, and its fiber is the 3 sphere. And then there's another one that lands in the 8 sphere, and its total space is the 15 sphere, and its fiber is the 7 sphere. These are the only fibrations that have this problem. The reason that there are so few is related to the construction of the Hopf fibration that I'm about to tell you about. So I'll explain maybe how these are all related to each other.
And that's it? Those are the only ones?
That's it.
It's a shame, there's such a pattern going on with the powers of 2 on the right side.
Yeah, absolutely, yeah. So it seems like there ought to be more of these, but in fact there's not, and there's a good reason that there's not.
Is it at all related to norm to real division algebra?
You get to ask that question in 3 minutes.
Okay.
So what I want to talk about now is the Quaternions. That already answers your questions. So probably everyone here is familiar with the complex numbers. So these are denoted with a blackboard bold C, and they're all numbers of the form A plus BI, where A and B are real numbers, and I is special. Right? Which just means that it's not a real number, it's something else. So B times I doesn't simplify any more than that. And in fact, this expression doesn't simplify anymore. And in order to explain how to multiply complex numbers, well, they multiply just like real numbers, except for there's one thing that's not clear, which is what is I squared. Okay? And I'll tell you what I squared is. It's minus 1. Okay, so understanding this fact, and that the rest of the arithmetic with complex numbers is, all the real numbers commute with I, and multiplication distributes by addition, etc. That completely describes how to do arithmetic with complex numbers. Okay, the Quaternions are similar. So these are denoted with an H. Does anyone not in graduate school or never been to graduate school know why H is the letter that's used here? It's named after a person.
Hilbert?
No, good guess. All right, keep thinking for just a second.
Think of the $10 bill. But not Sam.
So maybe as I explain them, it'll jog your memory, right? So the Quaternions have 3 special letters, special elements. Okay, so A, B, C, and D are all real numbers, and I, J, and K are special. How are they special? Well, I squared is minus 1, and J squared is also minus 1, and K squared is also minus 1. So I've told you some of how to multiply these things. Of course, I have to also tell you what's I times J. Well, that's K. And what about j times k? Well, that's I. And what about k times I? Oh, that's j. Okay. What about the other order? What's j times I? That's minus k. And k times j is minus I. And I times k is minus j. The way to remember it is when you interchange any two of these, you always get a minus sign. Okay? So with these rules, you can completely understand the arithmetic of the quaternions. Okay? It's a generalized arithmetic system. And the reason that it's named after a person is that this was a hard problem for mathematicians. There was this clear multiplication on the complex numbers. And the multiplication on the complex numbers is special. It's what's called a division algebra. It means that you can do cancellation in equations, right? So that's useful. The real numbers don't have a multiplication like that, or at least no one could find one. And they looked hard. They looked really hard.
Wait, say that sentence again.
Oh, sorry. The three-dimensional real numbers, R3 does not have a multiplication like that. Turns out the real numbers do have a multiplication. Okay. So yeah, maybe I should mention the real numbers up here. Right. And real numbers have a multiplication, but R3 does not. Okay. And a man by the name of Hamilton realized that if he added one more dimension, then he could get a multiplication that works out that has this division property. Okay, so these are sometimes called the Hamiltonians, if you like. The famous story is that he was so excited by realizing these equations that wherever he was walking under some bridge at the time, he carved these equations in the bridge at that moment. And if you go visit that town, you can see the carving there. It's exciting. Okay. There's I'll just tell you there's one other real division algebra. It's called the Octonians. Right, so the quaternions have dimension 4, and the complex numbers have dimension 2, and the real numbers have dimension 1, which I'll just remind you is 2 to the 0, and the Octonians have dimension 8. And then there's, right, so the fact that powers of 2 appear here is related to the fact that powers of 2 appear. And this last one that you get involves sort of a trick with 2 copies of the Octonians, so you have something in dimension 16. So we don't need to talk about that. I'll just tell you how the quaternions and quaternion arithmetic gives you this fibration eta. So the 3-sphere can be described as the set of all unit quaternions. So it's the set of all Q, and let me write it as W, this way, W plus Xi plus Yj plus Zk, such that W squared plus X squared plus Y squared plus Z squared is equal to 1. So this is, if you like tuple notation, you can call this W, X, Y, and Z. That just obscures how to do the arithmetic. It's not that hard. And so this set is the set of all points whose distance from the origin in 4 dimensions is 1. So this describes the 3-sphere. And yeah, and I've called these the unit quaternions because, well, because their multiplicative inverse is easy to write down. So for Q in S3, I claim that Q inverse is the following, right? So Q equal to W plus Xi plus Yj plus Zk. Then Q inverse is given by the same W, but then minus Xi, minus Yj, and minus Zk. And you can check that Q times Q inverse, well, let's just check it, right? So this is W plus Xi plus Yj plus Zk times W minus Xi minus Yj minus Zk. So how do you do this multiplication? Well, you have to distribute, right? So you get W times everything here, so that looks like W squared plus a bunch of other stuff. Maybe, you know, yeah. And then you have to do xi times all the stuff here. So that looks like, let's see, like wxi, and then, let's see, xi times minus xi, that's minus x squared times I squared, but then I squared is minus 1, so that's plus x squared. And I'm just going to do one more of these to illustrate that you have to use all the rules. Xi times minus yj, so that's minus xy times ij. Remember, ij is, I times j is k. So it's minus xy k. And a bunch of other stuff, right? And so you keep on going with this formula, and what you find is a bunch of stuff cancels, and what you're left with is w squared plus x squared plus y squared plus z squared. And by hypothesis, that was equal to 1. So this q to the minus 1 really is the multiplicative inverse of q. And the arithmetic is totally straightforward. In fact, if you have nothing else to do for the rest of the talk, then I suggest you can just work this out. It'll be easy. Okay. Now I'm ready to tell you what the Hopf map is. Okay, so I'll define a function, eta, from S3 to S2, and it's as follows. So for Q, unit quaternion, I'll just multiply Q times K times Q inverse. That's it. A priori, it's not clear at all that this lands in the 2-sphere, let alone in R3. This just looks like some other quaternion. And let me point out that if the quaternions were commutative, so if you could move all the i's and j's past each other, then this would just equal k, because it would be the same as q times q inverse times k, which would just be k. But the quaternions are not commutative, and in fact what you get is not k. So if you write out in coordinates, right, so you write q equals w, x, y, and z, you'll find that what you get is 0, and then the next coordinate is 2wy plus 2xz, and then 2yz minus 2wx. And then w squared plus z squared minus x squared minus y squared. That's just a straightforward application of the arithmetic. And what you can see, first of all, the magic here is that the first coordinate's always 0. Right? So this lies in the 3-dimensional subspace where w is equal to 0. So R3. Right? So the space where w equals 0. And what you can check, moreover, that if you square each of these numbers and add up those squares, you'll get exactly 1. So in fact, this is a point whose distance from the origin in R3 is 1, so this is in the 2-sphere. So in fact, this definition gives a map from the unit quaternions to the unit elements in R3, which is the 2-sphere. And I'll just say that the other examples of these fibrations arise in this. So I think that ends the arithmetic portion of the talk. Are there any questions about the question? All right. So the last thing I want to talk about before I start showing you pictures is about how to a visualization trick. And that trick, it's not really, it's a technique. It's called stereographic projection. So stereographic projection in 2 dimensions is a projection from the 2-sphere to R2. Except there's just one missing point. So we'll just add it in. I don't know what to call it. Maybe lazy 8 is a good name for it. Okay, so let me describe this projection, then I'll explain my choice of notation. So what you should think of is, here's the two-sphere, sitting in space. Think of the two-sphere actually sitting on top of R2. So here's a copy of R2, and the two-sphere is sort of sitting there. Maybe here's where the two of these touch. And now, what you can do for any point on the two-sphere, like let's say this one, is you can look at the line that goes from the North Pole through that point, and then continues down to the plane. So there's, think of it like a ray of light, right, just shining through there. And if you pick another ray of light, say this one over here, and you get some other point out there. And I mean, you can just keep on playing this game. It's so exciting, right? Pick a point on the back here, right? And there's so it sort of maybe lands up there. Oh, it's still bad. Maybe it lands there. Fine. One of the things you can see is that every sort of latitude line that you draw on the two-sphere is going to get projected out to some slightly wider circle in the plane. So maybe here's the equator that will get projected out to, let's see, I'll make my picture make sense. So something like that. All right. And likewise, right? So this circle up here gets projected out to outside the room. And likewise, lines that radiate up from the origin. So let's say this one passes through this blue point here. Those get projected to straight lines that radiate out from the origin in R2. So this one gets projected to that line there, etc. So this is, well, what does this do for you? It's a way of representing the two-sphere in a two-dimensional space, namely R2. The problem is that as you get closer to this top point, these lines get closer and closer to horizontal, and so there's a problem of where to send this yellow point. And so we send it to the extra point, and we call it infinity because, you know, it seems like it's going pretty far away from everything else. Okay. So that's stereographic projection in 2 dimensions, and I guess what I'll say is just that you can do the same thing in 3 dimensions. So, oh, well, I guess I want to do one thing, which is, right, there's a lot of stuff sort of far out here, so I want to bring it in for us. I just want to point out that R2, it's really big, but you could just imagine it as being the same as the open unit disk, T2. So this is the open unit disk with a point at infinity, but now the point at infinity is just this circle on the edge here. And that's, you're supposed to think of that as just a single point. And of course, if you try to actually visualize that, what will happen? Well, you'll have to sort of make a bubble out of that disk and collapse this boundary down to a single point. And what will you have done? Well, you'll have recreated the two-sphere. So it's the same idea as the two-sphere, but it's sort of, it's just brought in. Maybe I'll just mention that inverse tangent of x is a great function to use to collapse the real numbers down to an open interval, or R2 down to an open square. All right, so stereographic projection in 3 dimensions. Well, that's a projection from S3 down to R3. How does this work? Well, just imagine the 3-sphere. That was easy. Now imagine it sitting on top of R3, right? So in the 4-dimensional direction, it's just sort of on top of R3, which is just lying down here. And then just play the same game. Take sort of the North Pole and shine that light through all the different points in the 3-sphere, and it'll just be projecting them down to different points in R3, except of course the top one. So we'll just add a point over here for that one to go. And then use the same inverse tangent, or I feel like I should advertise. Hyperbolic tangent is another great function to use for this. just sort of bring this all back in to some bounded region. So now I'm drawing the unit ball in 3 dimensions. The open unit ball, that's why everything's dash, plus the point of infinity. Okay, so that's stereographic projection, and what I use in the video is stereographic projection to draw these fibers in the 3 sphere. So what you'll see is something that looks like a ball in 3 dimensions, plus, well, maybe we'll just think about that. So what is the Hopf fibration? It's a projection down to the 2 sphere, eta, and its fibers are circles. And what I'm saying is, using stereographic projection, you can replace this with the disk union a point at infinity, ball maybe I should say. And same old 2 sphere here. I'm not going to do stereographic projection here because we're pretty good at visualizing that one. And what do the fibers look like now? Well, most of the fibers are basically the same. They still look like circles. There's just one place where one of those fibers actually passes through this point, this north pole point. And so that one just looks like a line. But that's where the point at infinity is tacked on. Right? So when you tack on the point at infinity there, then that line is also a circle. Okay, so each one of the fibers is still a circle. There's just this special one that doesn't quite look like it. Okay, now's probably a good time for me to hit it on the wrong side. I'm just going to let this guy warm up. Right. And what I want to mention now is, well, I think I want to show you some pictures first. Oh yeah, will that work, Eddie, if I just...
I don't think so. I apologize for that. I don't think my computer will pump audio out of these speakers. I do not know why.
Okay, that's fine. What I want to do instead is, I just want to look at the pictures right now. So this is a picture. I'll let you win a prize if you can guess where I got this picture from. So this is a picture of a Hopf band. And you'll see lots of those showing up in the videos, so that's pretty fun. And then, let's move that page down. This is a professional drawing of stereographic projection. Okay, so same picture that I was drawing before. In my this one is a picture of some Hopf links. So the Hopf link is the boundary of the Hopf band. It's just 2 circles that are linked together. So there's a bunch of them here. So like this pink one is Hopf linked to all the other ones. This blue line is that special fiber that I was talking about. It doesn't look like a circle, but it is because these 2 points are both touching the point at infinity. And that goes in the circle. And then, well, so in fact, this is a phenomenon of the Hopf fibration, that every pair of circles, every pair of fibers are linked exactly once. So every pair forms a Hopf link. You can see that in this picture, and you'll see it in the rest of the pictures that I showed you. What's next? So here I wanted to explain, maybe I'll draw here, some things that you can look for in the video. So one of them is that torus. Above every point in the base, which is the 2 sphere in the base, if you have just one point, well, there's a circle above it. So this is in the joint space. And as I said, if you've got 2 points, then what you have above it is a Hopf link. if you've got 2 points with an arc between them, well, those 2 points give you a Hopf link, and the arc between them gives you a Hopf band. Maybe I should write it this way. Well, this is becoming impossible to understand. Right, so you get the Hopf band because every point along the way here gives you another circle. And those circles sort of interpolate to fill up a band. If you have an entire circle down here, right, so a bunch of points, and what you've got up above is a torus. So this is an example of a torus that sits above a bunch of points on a circle down here. And what's interesting, the torus that you see isn't constructed like a Cartesian product of the base with the fiber, because all these circles still have to be linked with each other, Hopf linked. And so the circle that lies above a particular point here sort of curves, it lies in a tilted way on the torus. Right? So you can see how these come around the outside and then they sort of go inside and around the back and back up to the front. So those are some of the things to look for. If you draw another sort of crazy curve down on the base, then you'll get some other surface. And it's interesting to see what surfaces you get. So now there are 3 things that I want to give a kind of scavenger hunt for. Okay, so 3 sort of advanced phenomena that when I play the video for you, if you see one of these, just write down the time that you see it at. And if you get all of them, then I have little prizes for you. So here are the 3 advanced things. So the first is the observation that, well, the 2-sphere comes from gluing together 2 disks. So the union of these 2 disks is the 2-sphere. And now what lies above each disk? Well, we've just said there's a torus above the edge of the disk, and in fact, every layer here, there's a torus above it, so there's a solid torus lying above one of these disks. I guess I'm not guaranteeing that this is lower and that's upper hemisphere. Well, I'm not saying it's not either. In any case, there's a solid torus lying above one of these disks, and another solid torus lying above the other one, and they're joined along their boundary. And the union of these 2 solid tori is the entire 3-sphere. So S3 is a union of 2 solid tori joined along their boundary. All right. The second thing also has to do with tori. I don't have a visual explanation of the base for this one, so I'll just write it in words. In the 3-sphere, a torus can be turned inside out. Without intersecting itself. So this is not possible in 3 dimensions, but it is possible in the 3-dimensional sphere. That you can turn this torus inside out without intersecting itself. If it's not clear what I mean, imagine a rubber band, like a really thick one. And you know how you can take that rubber band and just flip it so that what was facing inside is now facing outside, what was outside is now facing inside? That's the kind of flip you can do with the torus in the 3-sphere. You just flip it over. Like I said, you can't do that in 3 dimensions, but it's illustrated in the video. You can spot it. Okay, and then the third is the Hopf link is a fibered link. So I should tell you what that means so that you can look for it. What it means to be a fibered link is that there's a family of surfaces whose boundaries are the link. Maybe that's how the sound stopped working. So a family of surfaces whose boundaries are the link, and they don't intersect anywhere other than their boundaries. And this family is parametrized by a circle, S1. So a family of surfaces, each surface has the Hopf link as its boundary. So the Hopf band is an example of such a surface. But in fact, I'm telling you there's a whole circle's worth of these surfaces, and none of them intersect each other except at the boundary of this Hopf link. Okay. So